Imagine a world where machines don't just follow instructions, but learn to understand, reason, and even anticipate. That's not science fiction. That's the frontier of artificial intelligence today. And at the heart of this revolution lies a powerful idea: neural scaling laws. These aren't just curves on a graph. They're the hidden blueprint of how AI gets smarter as we scale up. But what are they really? And why do they matter more than any single breakthrough in architecture? Let's dive deep. We've all seen the headlines: models like GPT-4, Gemini, Claude, massive, powerful, seemingly magical. But behind the scenes, their success is due to one clever trick. It's the result of a systematic, predictable pattern. As you increase model size, data, and compute, performance improves in a consistent, measurable way. This is the essence of neural scaling laws. The first major insight came from a 2020 paper by DeepMind and Google researchers, Scaling Laws for Neural Language Models. They ran hundreds of experiments, training models of different sizes on different amounts of data, using varying levels of compute. And what they found was startlingly simple. Performance on a given task follows a power law relationship with model size, data size, and compute. Let's break that down. If you double the number of parameters in a model, say from 1 billion to 2 billion, you don't get double the performance. But you do get a measurable, predictable improvement. The same goes for data. Doubling the training corpus doesn't double accuracy, but it does boost it in a way we can now forecast. And compute. That's the fuel. The total flops floating point operations used during training. The more compute, the more you can train larger models on more data. And the scaling law tells us exactly how much better you can expect to do. The formula looks like this. Loss approximately C times N dash letter 1D43 times D dash letter 1D47 times F dash letter 1D9C. Where loss is the prediction error, lower is better. N equals number of parameters. D equals amount of training data. F equals total compute, flops. C of B, C equals constants determined empirically. This equation isn't just math for math's sake. It's a predictive engine. If you know how much data and compute you have, you can estimate how large a model you need to hit a target performance level. And vice versa. But here's where it gets even more profound. Scaling laws aren't just about language models. They've been observed across vision, speech, robotics, and even multimodal systems. The same principles apply. That means the scaling approach isn't a fluke. It's a fundamental property of how deep learning works. And that has massive implications. For researchers, it means we can plan experiments. Instead of guessing whether a bigger model will help, we can use scaling laws to decide. Should we train a 100 billion parameter model on 10 terabytes of data, or a 50 billion parameter model on 20 terabytes? The law tells us which path gives better returns. For companies, it means better resource allocation. You can forecast costs, timelines, and performance gains before you even start training. No more throwing money at bigger models blindly. But and this is crucial, scaling laws have limits. They're not infinite. At some point, you hit diminishing returns. The law predicts that performance will keep improving, but the gains get smaller and smaller. This is why the scaling hypothesis isn't a guarantee of endless progress. It's a guide to efficient progress. And here's a twist. Scaling laws don't just predict performance, they can also predict emergent abilities. That's right. As models grow larger and are trained on more data, they start to exhibit behaviors that weren't explicitly programmed. Think of it like evolution. Small changes accumulate and suddenly you get something new. For example, a model trained only on text might develop the ability to perform basic arithmetic just by seeing numbers in context. Or solve logical puzzles it wasn't directly taught. These aren't bugs. They're emergent capabilities. And scaling laws help us understand when and how these emerge. In a landmark 2023 study, researchers from OpenAI and others found that certain abilities, like chain-of-thought reasoning, code generation, and even rudimentary planning, tend to appear suddenly at specific scale thresholds. Not gradually, not randomly, but predictably. This isn't magic. It's math. The model reaches a point where its internal representations become rich enough to support complex reasoning. And scaling laws let us estimate when that will happen. Now let's talk about the elephant in the room. Are we hitting the limits of scaling? Some argue that we're running out of data. Others say we're hitting hardware limits. But here's the counterintuitive truth. Scaling laws suggest that we're not even close to the ceiling. Why? Because the data and compute curves are still growing. We're producing more text, images, video, and audio every day. And Moore's law may be slowing, but specialized hardware, TPUs, GPUs, custom AI chips, are pushing compute forward at a pace that keeps up. In fact, the scaling law itself is evolving. Researchers are now discovering compound scaling laws, where the optimal balance between model size, data, and compute shifts as systems grow. For example, as models get larger, you need relatively more data to keep improving performance. That's why recent models like GPT-4 were trained on trillions of tokens. This means scaling isn't just about going bigger. It's about scaling smarter. And that's where the future lies. We're moving toward efficient scaling, not just throwing more resources at the problem, but optimizing how we use them. Techniques like sparse activation, mixture of experts, and quantized training are already being used to stretch the limits of scaling laws further. But here's the deeper lesson. Scaling laws are not just tools. They're a philosophy. They tell us that intelligence isn't a single breakthrough. It's the result of systematic, data-driven progress. That the path to smarter machines isn't about reinventing the wheel, but about scaling what already works. So when you hear about the next revolutionary AI model, ask yourself, is it a new architecture? Or is it just bigger, trained on more data with more compute? More often than not, it's the latter. And that's not a failure. It's a triumph of science. Because the fact that we can predict how AI will improve before it even happens is one of the most powerful insights in modern machine learning. Neural scaling laws aren't just a pattern. They're a roadmap to smarter machines, to deeper understanding, to a future where AI doesn't just mimic intelligence, but grows into it. And that future, it's not coming. It's already here.